Hello everyone. Today I will discuss about some of the aspects of vibrational spectroscopy. So spectral regions and transitions. So infrared radiation induces stretching of bonds and deformation of bond angles associated with each vibrational transition for gas phase molecules, which is a series of rotational levels leading to the more complex rotational vibrational transitions. So this we call it as this is an example of water molecule, which we call it as a symmetrical stretch of H, O and H, and this is the symmetrical deformation of HOH, which is a bend form. This is an asymmetrical stretch which is caused between HO and H bond. So the simplest case of is a diatomic molecule which is causing 2 rotations and 3 translationals and leave only 1 vibrational degree of freedom. The bond length delta R as one-dimensional harmonic oscillator. So which can be solved by classical Hooke's law problem. So wherein the restoring force F will be equal to minus K delta R, and the potential energy for that is given by V is equal to half K delta R square. And quantum mechanically the energy of the vibrational level is given as EV is equal to V plus half H nu, where EV is the vibrational, V is the vibrational frequency. So a simple harmonic oscillator can be given by this model of harmonic oscillator can be given by for the vibrational spectroscopy. This is an harmonic diatomic molecule wherein the two end of the bond are given by 2 atoms. So according to the Schrödinger equation, EV is equal to V plus half H nu. So where delta V will be is equal to plus or minus 1. Delta E is equal to H nu according to Planck's equation. Therefore, small v is equal to half pi K upon mu raised to half. So the simplest form for a harmonic oscillator diatomic molecule, V is equal to half pi K upon mu raised to half, where K is called as force constant. In practice, the stronger bonds have a sharper or more curvature potential energy curves, which results the higher K and higher frequency, where mu is the reduced mass, which is given by M1 M2 divided by M1 plus M2. In practice, heavier atom moving have lower frequency. Vibrational frequencies reflect the structure, bonds and the atoms. So vibrational states and transitions. Summary: this high mass means low frequency, strong bonds means also high mass, low frequency, strong bond, high frequency. So these are the some of the frequencies for the bonds for stretches in polyatomics. This is a single bond 1000 per centimeter, carbon double bond 1600% to carbon triple bond 2200 per centimeter, carbon hydrogen bond 2800 per centimeter, carbon deuterium bond 2200 per centimeter, carbon nitrogen bond 1300 per centimeter. For a molecule of n atoms, there are 3n minus 6 vibrational degrees of freedom. This complex problem can be solved using the harmonic approximation by transforming to a new set of normal coordinates, combination of internal coordinates. To simplify the potential energy method, unimportant for the course, so which is given by this expression. This results in a molecular energy, that is the sum of the individual vibrational energies of the each normal mode, that is E is equal to sigma Ej sigma V1 plus half h nu 1. As a result, we have characteristic infrared and Raman frequency, so which are reflect bond type of the molecule. The frequency pattern forms a fingerprint for the molecule and its structure. Vibrations due to conformation and environment give a structural So in general, the interaction of light with the matter can be described as the induction of dipoles mu I and D by an light electric field E. So where E is mu I and D is directly proportional, V is equal to alpha E, where alpha is called polarizability. IR absorption strength is proportional to A psi mu f and mu final whole raised to square. Transition moment between mu1 and mu I and mu f. To be observed in the IR, the molecule must change its electric dipole mu. In the transition leads to selection rule d mu by dqi not equal to 0. Raman intensity is related to the polarizability, which is given by the below equation. So as its core, Raman also depends on dipolar interaction, but it is a two-proton process. Excite with V0 and detect Vs, where Vyb is equal to V0 minus Vs. So there are two mu's which are given by the following expression. Need a change in polarizability for the Raman effect. So this is a comparison given for the IR and Raman. So mu Vib is equal to Vn minus V0 delta E by H. Vib is equal to V0 minus Vs. Symmetry selection rules. Symmetric stretch. Infrared active. Raman active. Asymmetric stretch. Infrared inactive. Bending. Infrared active. These are the complementary of IR and Raman. For vibrational transition selection rules, harmonic oscillator, only one quantum number can change for on each excitation. Delta Vi is equal to plus or minus 1. Delta Vj is equal to 0. 1 I is not equal to j. These are the fundamental vibrations. Anharmonicity permits overtones and combinations. Normally, transitions will be seen from only Vi is equal to 0, since most of the excited state have the little population. Population Ni is determined by thermal equilibrium from the Boltzmann equation, Boltzmann relationship. Ni is equal to N0 exponential of Ej upon Ei minus E0 upon Kt, where T is the temperature in terms of Kelvin. Kt is at room temperature 200 per centimeter. So these are the this is the curve for anharmonic transitions. So real molecules are usually anharmonic to some degree, so that the other transitions occur but they are weak. These are termed as overtones. Delta Vi is equal to plus or minus 2, plus or minus 3, or combinations of delta Vi is equal to plus or minus 1, delta Vj is equal to plus or minus 1. So this is the curve from the harmonic. For the harmonic transitions, the curve will be parabolic. For anharmonic, it is slightly deviates from the parabolic curve. This is the Ed upon versus R minus Re. R is the bond length, Re is the equilibrium bond length. Thank you.